You may notice that we're going back to section 5.1. The order that the book gives us in, it works. It's just not my favorite for AB. So we skipped around a little bit. So today we're going to do section 5.1, which is on extreme values of functions. So we've been looking at local extremes, right? Where is it highest in some range or some domain? Where is it lowest in some domain? Okay, what we're going to be looking at today is absolute maximums and absolute minimums. Not just it's the highest one in this area or the lowest one in this area, but what is the highest over the entire graph or the specified domain. So let f be a function with domain capital D. F of c is the absolute maximum value of f on D if and only if f of c is greater than or equal to f of x for all x in that domain. Now let's stop before we talk about absolute minimum real quick. Notice that the absolute maximum is a y value. Okay, students frequently lose points because they only give the x coordinate. It's the y coordinate of the point that is the maximum or the minimum. So you can ask it two different ways. You can say, at what x coordinate does this have an absolute maximum? Or you can say, find the absolute maximum. Two different questions with different answers. Okay. Conversely, f of c is the absolute minimum value of f on D if and only if f of c is less than or equal to f of x for all x in D. I also want to point out that it says or equal to, right? The absolute maximum or the absolute minimum can happen over and over again. Take, for example, a function you're really very familiar with, the graph of sine of x. The maximum value of sine of x is 1. But over its domain, that happens an infinite number of times. But it's the greatest value that you can possibly turn out. Some books call these global maximums and minimums. Absolute, global, same thing. So a lot of times, though, they won't ask you for absolute or global. They'll just say find the maximum or the minimum. And that's to be understood to be the absolute or the global maximum or the global minimum. So the extreme value theorem, we talked about this briefly the other day. I said we're going to get to this. Here we go. If f is continuous on a closed interval from a to b, then f has both a minimum and a maximum value on that interval from a to b. So when we have continuous functions, you're going to have a maximum and you're going to have a minimum. Now the question is, well, how can we find where they are if we're not looking at the graph and going, oh look, that point's higher than all the other points? So here's where to look. Extreme values of a function occur only at critical points or endpoints of the function's domain, although not every critical point or endpoint signals the presence of an extreme value. So what we've been doing so far is we've been just looking at the interior of the interval and looking for local maximums and local minimums. Now we're going to look at the interior of the interval and at the endpoints of the interval if there are any. We'll talk more about the if there are any later. This leads us to something wonderful, which your book doesn't call the candidates test, but every person I've ever talked to about this subject calls it the candidates test. It says, if f is continuous on the closed interval from a to b, and has critical points between a and b, x is c1, x is c2, etc., 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 through c sub n, then the maximum and minimum values of f on the closed interval from a to b may be selected from f of A, f of B, f of C1, f of C2, blah, blah, blah. In other words, those are your candidates. Those are your possible maximums and minimums. So the nice thing about this is you don't have to do the number line. You don't have to test if it's a local maximum or a local minimum. We're just going to, once we've identified the candidates, we're just going to see by substituting in which one is the greatest and which one is the least. Okay, in some ways this is actually easier than what we've been doing before. Sometimes it takes a little bit longer, but let's take a look at some. So notice the maximum and minimum values. Again, that's understood to be the absolute maximum and the absolute minimum. So we'll take the derivative, f prime of x, and that's 2/3 x to the negative 1/3, or 2/3 cube roots of x. Remember, critical points are places where the original function exists and the derivative is either 0 or is undefined. Where is this undefined? At x is 0. Where is it equal to 0? It's never equal to 0. Trick question. All right? So this does not exist at x is equal to 0 and is never, and f prime is never equal to 0. So you're literally going to make an old-fashioned Algebra 1 T-chart with x and f of x. We're testing to see where the function is the greatest. The number of times I've had a student accidentally put f prime in here and they find, that f prime doesn't exist at x equals 0, and I'm like, yeah, we already know that. We're testing to see where the greatest value of f is and where the least value of f is. So they could occur at -8 or 1, or it could occur at 0. So -8, see, -8 to the negative 1/3 is -2. Excuse me, it's -1/2, because it's in the, wait, back up to here. I just did what I told you not to do, didn't I? Oh, there's a great, I don't know if any of you have read it. There's a Berenstain Bears book, which is it's a kid's book, and the dad is trying to teach his kids how to do things, but he keeps screwing it up. And it's like he crashes and he's like, that's how not to ride a bicycle. And so anyway, all right, so if we take -8 to the 2/3 power, that means take the cube root, that's -2, squared is 4. 1 to the 2/3, that's 1. 0 to the 2/3 is 0. So that means that the maximum value is 4. And the minimum value is 0. Yeah. All right, let's find the maximum and minimum values of this function f of x on the closed interval from -4 to 2. Notice it has to be a closed interval for this, right? It has to be this closed domain in order to use the candidates test. So we'll take the derivative. F prime of x, we'll get to use the quotient rule. Woohoo! So it's 1 plus x squared times 3. minus 3x times 2x, all over 1 plus x squared quantity squared. Just like we've been doing, look first to see if there's a place where the derivative doesn't exist. Is there a place where the derivative doesn't exist in the real numbers? No. The derivative always exists, so we're just interested in setting the numerator equal to 0. So that's 3 plus 3x squared minus 6x squared. So we're going to have negative 3x squared plus 3. I'm going to factor out a negative 3 out of that so that I get a positive coefficient on my x squared term. You can either factor this or think about it for a second. X has got to be what? Or, yeah, positive or negative 1. So I have 4 candidates this time. And again, we never have to do any checking for locals. We're just doing the absolutes. So negative 4, 2, 1, negative 1. Let's see, negative 4, that'll be negative 12 over 17. Ugh. At 2, that'll be 6 over 5. At 1, it'll be 3 over 2. And at negative 1, it'll be negative 3 over 2. All right, so for the absolute maximum, it's either going to be 6/5 or 3/2, but we immediately know which one's bigger because 3/2 is bigger than 1, 6/5 is not nearly as much bigger than 1. So the maximum is 3 over 2. And for the minimum, see, that's negative 1.5. That's not even negative 1. So the minimum is negative 3 over 2. It turns out that the extremes happened at the critical points. Sometimes they happen at critical points for both of them. Sometimes it's one of each. You never know. So the question becomes, well, what if you don't have a closed interval? If you don't have a closed interval, you have to use something that, again, your book doesn't call it this, and not all textbooks do, but I always have. I call it the lone candidate test. It says if f is continuous on an interval from a to b, open or closed, doesn't matter, and x equals c is the only critical point on the interval, then f has an absolute maximum of f of c if f has a local maximum at x equals c, and f has an absolute minimum of f of c if f has a local minimum. So we're going to start with a local argument, and if it's the only critical point, then we can move that to a global argument. This is the only time you can do that, is when you only have one critical point. If there's more than one critical point, absolutely cannot do this. So, for each function, find the maximum and minimum value, if they exist, on the domain given. Justify your answers. All right, so we'll take the derivative of this. So f prime of x is going to be 3x times cosine of x minus sine of x times 3 all over 3x quantity squared, which is 9x squared. All right. Is there a place where the derivative does not exist? 0. Is that a problem for us on this problem? No, because it's not in the domain. So we don't have to worry about that. So we need to look for a critical point between 0 and 3. So the critical point, I only need the numerator to be 0. That can make what you put into the calculator a little bit simpler. It'd be 3x cosine x minus 3 sine of x. I was telling you guys about the NumWorks calculator. Let's see, window. There it is. I don't want to be showing everybody's grades. I am. I'm really bad still, but I'm learning.
Play in our orchestra.
Pardon?
Play in our orchestra.
Is that an invitation, or somehow I think I would be overwhelmed by what you're doing at this point.
You got it.
All right, so go ahead and graph that on yours. I'm going to graph it on here. So this is 3x cosine of x minus 3 sine x. I like it. It automatically puts the y equals in there. And if I go to graph this, it's going to give me a window that shows a lot of the important stuff automatically. I don't have to set that. But I want this to only be between 0 and 3, right? So I can go up and go, okay. I can change the axes. I want values of x only between 0 and 3. And values of y, since I want to see the zeros, sort of like what we do all the time, do like from -1 to 1. Oh, hang on just a second. Oh, I have to come. I don't like this that you have to come down here and confirm it. Is there no 0 between those two?
Graphing 3x times cosine of x minus 3 sine of x.
Yeah. Hang on just a second, see if I put something in wrong. Three x cosine x minus 3 sine x, yes? Should be doing radians. So where did you get your 0?
Can't find my cursor.
I've done something wrong, I just don't know what it is.
0.321 and another one that's at 0. Yeah, I have mine at 0.321.
You got it at what?
At 0.321.
0.321?
Yeah.
All right. I'm not going to spend more time looking at what I've done wrong. 0.321. So that is my only critical point. So if I'm looking between 0 and 3, at 0.321, my derivative is 0. And was it positive or was it negative between 0 and 0.321? I think it was positive looking at your graph.
Yeah.
So f prime is positive here, f prime is negative here. So since f prime changes from positive to negative, at x is equal to 0.321, f has a local maximum at x equals 0.321. So make the local argument first, just like we've been doing. And since the only critical point of f on the interval from 0 to 3 is 0.321, f of 0.321, which you would have to substitute back into your calculator to look at something, is the absolute maximum. So make the local argument first, then you can make the global argument. All right, you guys have a good one.